next talk in the session will be on SparseAuto, auto-scheduling sparse tensor computations using recursive loop nest restructuring. And Adhitha Das will be giving the talk.
Hello. Good afternoon, everyone. I'm Adhitha from Purdue University. I will be presenting our work on SparseAuto, auto-scheduling sparse tensor computations using recursive loop nest restructuring. This work was done in collaboration with Logan, Anderson, Kirshanthan, Sundararajah, who is also here today, Artem, Pelenitsyn, and my advisor, Milind, Kulkarni. Sparse tensor computations are used abundantly in graph neural networks, quantum chemistry simulations, data analytics, and linear algebra applications. It turns out that doing a good job of scheduling tensor contractions is really challenging. Let's look at this tensor times matrix multiplication contraction. For simplicity, let's say all of these tensors are dense. We can realize this computation with 6 perfectly nested loops. We call this materialization a schedule. The asymptotic time complexity of this computation would be O of lmn ijk. For instance, let's say now B is a sparse tensor. I have bolded B to show that it's a sparse tensor. Notice how the loops in the computation have changed with B's index arrays now. When B is sparse, the time complexity of the computation now becomes O of lmn times non-zero values of B instead of lmn ijk. Analogous to chain matrix multiplication, we can split the previous computation to 3 separate tensor contractions and still obtain the same final result. Now, this sort of schedule has lesser asymptotic time complexity compared to the previous version with 6 perfectly nested loops. But this splitting process adds extra temporaries. Notice the 2 3-dimensional temporary tensors we have used in the computation. These big temporaries could make the schedule inefficient. Here, we can fuse some of the loops in the previous schedule and obtain an imperfectly nested loop structure. While the asymptotic time complexity of the schedule remains the same as the previous one, the auxiliary memory complexity goes down because after fusion, only 1 2D and 1 1D tensors are used, as compared to the 2 3D tensors we had in the previous version. So now, how do we pick one good schedule or a few good schedules out of all the schedules in the schedule space? To pick a good schedule, 3 things need to be done. The first is enumerating the schedule space to generate all the loop schedules. The second is pruning the search space to a manageable few schedules using asymptotic time complexity and auxiliary memory complexity. And the third part is realizing a schedule. We do this by extending the scheduling language, which I will not cover in this presentation. For details, please read our paper. Let's move on to the first part of the presentation, schedule generation. For this part to work, there are a few moving parts that need to come together. Tensor algebra compiler can generate code for sparse tensor algebra. It can generate the linear loop nest we saw earlier. Then they introduced adding intermediate workspaces to the tensor computation. And later, the branch iteration graph concept was introduced, extending the scheduling language of Taco. In this work, we further extended so that we can apply the transformation recursively to arrive at multiple levels of imperfectly nested loop code. I want to reiterate how schedules are realized depending on the choices we make and how it leads to a lot of different schedules. The first question we need to ask is, where do we break the tensor contraction? For example, in this expression, we see that we can choose to break between B and C, between C and D, or between D and E. If we choose to split the computation between C and D, we would realize the schedule like this. The next question that we can ask is if we should fuse the loops. For example, we can notice that both these loop nests starts with loop L. And this can be fused to reduce the temporary memory. Fusing the loop L can be realized this way, reducing the temporary memory from 3 dimensions to 2 dimensions. The next question is if we should reorder the loops. For example, we can change the order of the loops njk to kjn. The last but not the least, we can ask if we can do the previous 3 steps recursively. Focus on this square. If so, it may lead to multiple levels of imperfectly nested loop code. All these decisions leads to a lot of different schedules, which could be in hundreds of thousands. So in part 2 of my presentation, I talk about pruning this large schedule space to arrive at a manageable few schedules. We can choose to prune the schedule space at runtime, but there are just too many schedules. And if we decide to choose a schedule at runtime, it's just gonna take a lot of time. So we need to come up with a cost model to prune the large search space at compile time. RNs in their PLDI22 paper uses a time complexity to prune the search space. In this work, we also consider auxiliary memory of a schedule to prune the search space. At certain instances, we observe that schedule with better memory complexity and reasonable time complexity can beat the schedule with the best time complexity and vice versa. So there are 5 stages in our TOS scheduling pipeline, 3 stages at compile time and 2 stages at runtime. Let's run through all of these stages one by one. The first stage of pruning at compile time is the memory depth-based pruning stage. This stage uses a heuristic called memory depth. For example, if the maximum dimension of the temporaries in a schedule is 3, we say that the memory depth of that schedule is 3. For most practical scenarios, tensors with 3 or more dimensions are too big as temporaries. So in this stage, we remove all the schedules having temporaries with 3 or more dimensions. The next stage of our pipeline is based on both loop depth and memory depth. We take loop depth as the maximum nesting depth in our imperfectly nested loop structure. We consider the partial order of these 2 criteria. Let's say we have some schedule S with a loop depth of 5 and memory depth of 1. And another schedule U with loop depth of 6 and memory depth of 1. In this case, although schedule U has the same memory depth as schedule S, schedule U has higher loop depth. So we choose to prune the schedule U. Let's take a different schedule V. In this case, schedule V has the same loop depth as schedule S, but schedule V's memory depth is high. So we remove schedule V also from the schedule space. And there can be other schedules like schedule W, where it is better in terms of one of the criteria, and it is worse in terms of the other criteria. So in this case, we say that these 2 schedules are incomparable, and we don't prune any of the 2 schedules. In this step, we use the symbolic expressions of time complexity and memory complexity. For example, a schedule could have a time complexity expression such as LMN times non-zero values of B, and an auxiliary memory complexity expression such as KJ. We use these expressions to compare against another schedule's time and memory complexity, symbolic expressions. For this stage, we need to have some other inputs as well. We assume that some information about the computation is readily available at compile time. For example, if we are using this in a graph neural network application, we would know that the feature size would vary between 64 and 256. We call these constraints range constraints. Also, we know that the number of non-zero values in a sparse tensor would be lesser than its dense counterpart. We call these type of constraints inferred constraints. And there can be other user-defined constraints. For example, the user could know that index J's bounds is less than 10 times that of index I's. Going back to our schedule space, let's assume there are 2 schedules S and U with different time and memory complexity expressions. We input these expressions along with the other constraints to an SMT solver. And we ask the SMT solver if time and memory complexities of one schedule dominates the time and memory complexities of another schedule for all considered value ranges. If schedule has lower time and memory complexities for the entire value range, then we prune the schedule U from schedule space. Sometimes schedule S could be better than schedule V for some value range, and for some other value range, schedule S could be worse. In this case, we say that they are incomparable and keep both the schedules for the next pruning stage, and we make sure that we don't over prune the schedule space. Let's move on to the first stage of our runtime pruning stages. During runtime, we have the concrete bounds of the tensors and information like the number of non-zero values of the sparse tensors. So we can evaluate our time complexity expression and obtain a concrete value, which we call the evaluated time complexity. We keep all the schedules with the minimum evaluated time complexity and remove all the other schedules. The second stage of the runtime pruning is based on the cache access complexity. Here, a schedule would have good cache access if the tensor's data access pattern matches that of the loop order in the computation. If they have different orders, then the cache access does not have good locality. So in this case, we first find the minimum evaluated cache access complexity of all the remaining schedules and only keep the schedules with the minimum evaluated cache access complexity. Now you end up with a handful of schedules that are good in terms of both time and memory complexities. Now you can run your computation on one of these schedules. That concludes our pruning stages. Now let's see how well our system compares against other state-of-the-art auto-schedulers and how auxiliary memory affects performance. We evaluate 8 different contractions that can be split to meaningful kernels, such as the sample dense matrix multiplication, sparse matrix multiplication, or sparse tensor times matrix multiplication. And we evaluate these kernels on real-world tensors. We report the execution times and speedups comparing our schedule with Taco default schedules. Results for sample dense matrix multiplication, sparse matrix multiplication contraction is shown on the left. This kernel is used in graph neural networks. We see that SparseAuto selected schedule is orders of magnitude faster than Taco. The plot on the right shows the results after adding gem kernel to the first computation, extending it. We see that now the speed up varies between 40 and 140 for the same data sets as compared to 5 and 8 before. This shows the gains our framework gets by optimizing for asymptotic time complexity. We also compare our framework with Pigeon. We see that we perform better for some tensor contractions. We also see that our framework doesn't do well for some other kernels. We do not always win because our cache model doesn't appear during compile time, and it is not sophisticated enough. So during compile time, our framework could potentially prune some good schedules that could do well in cache utilization. So we stress that having a good cache model benefits an auto-scheduler. We also compare our framework with SPTT and Cyclops by changing the dense dimensions L, M, and N in the tensor times matrix contraction. The auxiliary memory used by the schedule chosen by our framework is M+1, and the auxiliary memory used by the schedule chosen by Cyclops is Mn+n. In both the frameworks, the time complexity is the same. The number of accesses to these newly introduced temporary tensors is proportional to L. We see that Cyclops does well when the temporary tensors are small and they are not accessed frequently. But when they are large and accessed frequently, our framework does better. If we use a bigger data set like Flickr 3D as compared to a data set like NEL2 in the first plot, we see that our framework has clear gains compared to Cyclops. These plots show how the schedule selected by our framework performs when compared with all the other schedules in the schedule space of SPMM gem kernel. We can see that the schedule selected by SparseAuto is within the top performing 5% of schedules. The schedules you see in red are the schedules with the lowest evaluated time complexity. We can see that they use a lot of auxiliary memory and do poorly compared to the top few best performing schedules. Details on the effectiveness of the pruning stages and details about parallel execution and scaling, the effect of skipping certain stages, and how long each stage takes to execute can be found in our paper. In this talk, we saw how the memory consumption becomes an important factor in choosing a good performance schedule. We saw how the schedule space can be partially ordered based on time and memory complexities to prune the schedule space. and how it can be used to create a robust Pareto frontier and avoid overpruning. Using an SMT solver with partially known parameters at compile time can further prune the search space, and it can give wins at runtime. We also stress that auto-schedulers would need to consider more criteria, like cache access patterns at compile time. Thank you. I'm happy to take any questions that you may have.
Questions? Okay, I can start. Your evaluation was on a particular CPU. Is your framework parameterized, I guess, by cache sizes and other properties of the particular CPU? Like you do need to rerun the optimization if you were doing it, I don't know, on an AMD chip or something like that?
So during our compile time phase, we prune most of the schedules. So by the time you get to runtime, there'll be only a handful of schedules left. So these are good in terms of both time and memory complexities. But we also do prune some schedules if they use a lot of memory based on the cache size. So you need to know the cache size of your machine. But it doesn't have a big effect, as most of the schedules that are left to be evaluated during runtime mostly uses a lot less memory compared to all the other schedules that you pruned out.
Okay, we have another question.
Hey, thanks. I really enjoyed that. There's also maybe some opportunities for tiling and strip mining and this sort of stuff. Have you considered that?
Yeah. So auto schedulers, maybe I should. So these are the number of schedules for each of those kernels. So it depends on the number of input tensors you have and also the number of indices in each of the tensors. So we get these numbers with just changing the loop order. But if you start going, adding all those scheduling directives like parallelizations, blocking, and all the other things, the schedule space is going to blow up. And also, you would need to come up with more clever ways to, prune the schedule space. We haven't looked at it. As compared to RN's PLDI22 work, they only look at time complexity. We look at 2 axes in this work. I guess in the future, you could start adding more criteria for compile time pruning. But I guess it would require clever ways of pruning and handling schedule generation and whatnot. Good question.
Thanks for the great presentation. I was wondering, at which time do you specialize to the particular sparsity pattern of the data as well as the input dimensions? Is it the completion time or runtime?
So in this work, we don't really care about the sparsity pattern. We assume that it is uniformly distributed. But I guess you could do some sort of optimization based on the sparsity pattern.
How about the dimensions? Because for different input data sets, you could have priority for another schedule, let's say.
Sorry?
So whenever you change your input tensors, so it could be the case that a different schedule is going to become.
So in our stage 3, the user gives some information about the ranges. So if this range is going to change a lot, you would need to run the stage 3 again and then get a different set of schedules so that you can find one schedule from those during runtime.
Okay, but it's only the dimension then. By range, you mean that the kind of dimension at different order of
dimensions
tensors.
Or even sparsities.
Okay, thank you.
Thank you.